I will talk about polar coding in this talk and how to improve that performance at short block length regime. So this is a joint work done by our previous postdoc Baccelli and Jean-Yves Baudet and Anne Savard. Okay, so here the outline of the presentation. I will start by a gentle introduction to polar coding, stating the basic principle of encoding and decoding process. Then I will do a little review of the state of the art on the works that have improved the performance of this kind of code in a finite block length regime. Then I will go through a proposal that we did this time on precoding scheme based on Reed-Muller coding. Then present the main results and the supporting simulations that goes with the proposal. Okay, here we go. So this is the fundamental block of a polar coding. Okay, this is a polarization kernel proposed by Arikan in his milestone paper in 2009. So where we have two input bits, U0 and U1, that is coded to the two coded bits X0 and X1 through this polarization matrix. Eventually, this coded bits go through binary discrete memoryless channel. So for instance, a binary erasure channel with erasure probability delta. If we go with sequential decoding, so we first decode U0 and after U1, then U0 fails to be decoded if X0 or X1 are erased. And this happens with probability 2 minus delta by delta, which is strictly greater than delta, the original erasure probability. After, if U0 is decoding correctly, we can retrieve U1 by observing X1 or by combining U0 with X0. So an error of decoding will appear if and only if X0 and X1 are erased, which arrives with the probability delta square, which is strictly less than the original binary erasure channel. So this is a striking observation made by Arikan. So we have two synthetic bit channel, one that is worse than the original one, and the other that is better. So this block can be extended to any block length of power of 2. So for instance, here for a block length equal to 8, so it is a 3 times Kronecker product of the original polarization kernel. So for instance, if we have this information vector, we have this coded vector. And so if we extend the reasoning that we made for the binary erasure channel with the fundamental polarization kernel G2, we realized that all bits do not have the same erasure probability, the same probability, yes, to be not decoded. So for instance, the bits U0, U1, U2, U4 have this probability to be erased. This is equivalent that if they pass through a binary erasure channel with this erasure probability, and the other bits have another probability, rather much less, probability to be erased. So this is an evaluation made for an original erasure probability 1/3. Okay, and so we remark that we have some bits that are erased with really high probability in green, and other that are transmitted more or less all the time. So naturally, the bits in red will convey information, it will be the information bits, and the bits in green will be inactive, do not convey any information. They are what we call the frozen bits, and they belong to a frozen set. So What about the decoding? So the polar coding proposed by Arikan comes with a particular decoding, the successive cancellation decoding, that we will go through right now. So if we take an example, so we take a node T, okay, and the principle of the successive cancellation decoding is a message passing iteratively between nodes of a tree. So this node at T will receive 2 to the power T soft input elements coming from the upper layer. For instance, it can be LLRs, log likelihood ratios. It will provide to his left-hand child node 2 to the power T minus 1 soft input elements, which is a function of the input element coming from the upper layer with a function f that depends on the channel, Gaussian, binary symmetric, erasure, etc. So for instance, if it is a binary erasure channel, this is a XORing function. This left-hand child node takes a hard decision, and it comes back to this node at T. This hard decision is combined with the soft input coming from the upper layer to produce the 2 to the power T minus 1 soft input elements according to a certain function G that depends also on the channel. And for instance, if it is a binary erasure channel, this is a combination of a XORing function of the hard decision coming from the left node, the soft input element coming from the upper layer, and also logical OR. And they produce the hard decision that will, after, escalated to the upper layer thanks to a XORing function depending on the hard decision coming from the left and the hard decision coming from the right. So let's take a toy example to see how it works, this. So for instance, if we take the information vector and the coded vector that we mentioned previously, U and X, we observed the vector Y, which has 3 erased elements noted by E. So we have a decision tree. We have a tree like this, so with 4 levels. And at the ground floor, this is the leaf node having the decided bits. Okay. So we have some bits that are frozen. So it means that it is known from the decoder. Okay. And this is they are fixed to 0. So we start by computing the soft input element coming from the first edge, left edge of the tree. So that has 4 elements. So depending on the XORing function of the elements of the incoming vector. Then we continue on the left, also by XORing the elements of this vector. We also have the soft input element coming from here, but it does not really matter because we already know the hard decision here since it is a frozen bit. And this hard decision is combined with these elements in order to produce this hard decision. But again, the hard decision is already known since it is a frozen bit. But we need this in order to achieve the other leaf node, since it is a sequentially decoder. And like this, we can resolve the erasure event here and computing after the soft input elements going to the level 1 through to this function. And thanks to the hard decision here and soft input here, we have our first decision of the information bits, which is U3 equal 1. And repeating the operation, we get all the information bits. So this is the basic successive cancellation proposed by Arikan in his seminal paper. However, it performed relatively bad compared to maximum likelihood decoding, which is the optimal one. So in 2015, Tal and Vardy has proposed their so-called least decoder. And the idea of the lead decoder is to let several successive cancellation decoders working in parallel. So each time a leaf node is reached, the bit is estimated as both 1 and 0, doubling the number of code words candidates. So we will have several paths. So the idea is to keep the most reliable path in order to have a metric to decide which code words have the most probability to have been set. And these perform relatively close to the maximum likelihood detector. So applying this scheme, it creates n bit subchannel, what we can call the bit subchannel. So the bit subchannel is a transformation of a bit at stage I, ui, to the observed vector and the I-1 previous decoded bits. Okay. So the striking observation made by Arikan is that if we apply this coding and decoding scheme and n goes to infinity, the proportion of bit subchannel, whose capacity is larger than 1 minus delta, tends toward the capacity of the original binary eraser channel. Same way, those whose capacity is less than delta tends toward 1 minus the capacity of the original binary eraser channel as n goes to infinity. So the channel polarized. So here we reproduce well-known results on the mutual information of the different bit subchannel according to the index on the left of each subchannel, and for n equal 1024. So we see that we have some bit channels that are really good or some that are really bad. And here on the right, we see the polarization effect of the channel. So this is where the index are sorted according to the number of code lengths. Okay, so it polarizes. The channel polarizes when n goes to infinity. It will go to a perfect Heaviside function. Okay, so if we step back a bit on the application of this coding, so if we look at the main use case of 5G networks and also beyond, we have at least two important features, which are the latency and the reliability constraint. So for instance, for communications like ultra-reliable low latency communications for autonomous vehicles, for instance, we will have really stringent latency and reliability constraint. So for latency constraint, reliable short block length code are important in order to limit this latency, and we have to make them relatively good, so that have a low bit and frame error rates. So the problem is that in the previous slide, I just show that polar codes are not good at short block length because the channel polarizes at infinite block length. So why talking about short block length? So first, there is two reasons about this behavior. The first one is that the structure of encoding of polar codes impose poor minimum distance of the code. At least the one proposed by Inria. The second one is that the successive cancellation decoding is there is a gap between the maximum likelihood decoder and the successive cancellation decoder. So this gap has been partially solved, at least in 2015, with the least decoder. The least decoder, when the least size increases, almost close the gap with the maximum likelihood decoder. So the question is, can we build efficient, so it means with relatively high rate and low frame error rate, short polar codes? So let's see what we have in literature. So in 2015, we already talked about the work of Tal and Vardy. So they propose, in addition to the original polar codes, an outer code, a cyclic redundancy check code that allows to improve the decoding process by eliminating the wrong path in the decoding tree. Trifonov and Milovskaya have proposed their polar subcodes in 2016, which is an extended BCH code that that generalize the principle of outer code. So with the inner code, we have an outer code that it is precoding. So it shapes the distance spectrum of the polar code. So this is the idea of the precoding scheme. And they introduce a really interesting concept. This is dynamic frozen symbols. So in the Hurricane work, the frozen set are chosen as less reliable bits. Okay. With dynamic frozen symbols, we allow to fix the bits as function of the previous information bits. So that's very important. In 2019, Hurricane proposed his PAC codes, so the polarization adjusted convolutional code. So it is still a precoding scheme, but with a particular matrix T, which represents a convolutional encoder, so a rate 1 convolutional encoder. And it performs relatively close to the second order rate approximation of Polyansky with list size decoding. And in 2020, also, Miller-Slavskaya and Vucetic has proposed to directly optimize the precoding matrix directly to minimize the bit error rate, which is the criterion that we want at the end optimized. If we look a bit what we have in the standards and actual systems in 5G, so polar codes have been adopted for control channels, so they are used for control channel. The idea of the coding scheme that implements polar codes in 5G is explained as follows. I will say a word on that. A path in the successive cancellation decoder, list decoder, can be seen as a subvector U02 I-1. And at the I stage, the decoder tries to choose I1, UI equals 0 or UI equal 1. So we either the former one is a coset is called the coset 0, and the later one is a coset 1. So JJ is the jth row of the polarization matrix. So what is important is the distance spectrum between these cosets. The distance spectrum between these cosets control drives the performance of the successive cancellation list decoder. So this distance spectrum is the number of code words whose Hamming weight is equal to W, such that they correspond to all 0 decoded bits pass except the ith one, which is 1. Okay. And if there is the bit position does not involve parity equation, then this Hamming weight, this minimum Hamming weight, is the Hamming weight of the G flow of the ith row of the rows of the information set. So the idea developed in the 5G standards is the parity check coding, and this is to let the ith bit be a linear combination of previous information bits. And that's why we can tune the value of this bit, and we can increase the Hamming weight of the combination, and so the distance spectrum of the code to make the different successive cancellation list path more distinguishable to one the others. So a quick example is this one. So if we take n equal 16, so the code word equal 16, the two rows 5 and 10, whose Hamming weights are equal to 4, we impose the frozen dynamic function u5 equal u10, then this combination produce a new a part of code word that Hamming weight is equal to 6. So we increase the Hamming weight and shape the distance spectrum of the code like this. So the idea is to reserve just enough polar parity check bits from the most reliable subchannel. So it does not choose the information set the same way than Hurricane proposed. Okay, we reserve some bits from the information sets for the parity bit. Okay, but this will allow to shape the distance spectrum of the code. So the question is, can we design a parity check like polar codes with higher minimum distance and also with some systematic way to construct this kind of code? So this is the point of our proposal. Okay, so just few notations that I will need later. So Bj is a binary representation of index j on n bits. P1 is the index set of ones in the vector x. P0 the index set of zeros. Boolean or, Boolean and are noted like this. And the Hamming weights of vector x is noted I1, so this is the number of 1 in x, and the number of 0 is noted I0. Okay, so a polar-like code is a polar code, but where we let the choice to choose the frozen set in a different way than Hurricane proposed. Okay, so the information set is a complementary of this set. And an important thing is that the Reed-Muller code of degree R is a polar code, actually, can be seen as a polar code, where the information set has this particular form. So this is the union of a set. And this set, NP, is a set of indices whose Hamming weights of the binary representation of this index are equal to P. And it has been proved that the minimum distance of a polar codes, of a polar-like codes, is related to the minimum distance Hamming weights of the rows belonging to the information set, which is linked to the Hamming weights of the binary representation. Okay, so in our case, we will talk now about row merging. And what we call a row merging is a precoding scheme. So with a matrix T, so we have the polarization matrix G, which is a classical construct with the classical Hurricane kernel, the precoding matrix T. In our case, we construct the matrix T such that the number of ones in particular column is at most equal to 2. And this corresponds to those columns belonging to the frozen set. So in that case, we call it row merging technique. The scheme is built on a careful look of the structure of each rows of the matrix J, the polarization matrix. So each row, the row G of the polarization matrix, can be written as a Kronecker product of subvectors. So JJ is a concatenation of subvectors RGL, whose RGL is either a bunch of zeros, if BGL equal to 0, and if BGL equal 1, it is the repetition of the previous subvector. So this is a particular structure of the polarization matrix. For instance, if we take G6, so G110, B60 is equal to 0, so it is 10 here. B61 is 1, so RG1 is a previous subvector. B62 is 1, so RG2 is a repetition of this. And this allows to define the set ML that identify the zeros, the position of zeros in the row of the polarization matrix. For instance, M0 is 1, 3, 5, 7 because B60 is at this position. And the structure, we can prove that the structure of this set as this particular expression. Again, for M1, we have this position of zeros, and M2, this position of zeros. So this is important to construct our particular design. A preliminary theorem that is important is that it states that the Hamming weight of a combination of any rows of the polarization matrix is lower bounded by the maximum of the Hamming weight of a subsum of the rows of the polarization matrix corresponding to the zeros at position L. So for instance, if we take n equal 5, we have this three line, 11, 18, and 5. And the summation, the Hamming weight of the summation of the rows 11, 18, and 5 is necessarily larger than the Hamming weight of G18, because we have a 0 here. It's larger than the summation of 11 and 18, and so on. And thanks to this theorem, we can state the first important result, stating the minimum distance of a code with row merging without common one bit in their binary representation. So if we take a triple, okay, I take directly the example, a triple IGK, so without any common one bit position in their binary representation like this, then we can construct another polar code by putting the information bits to the combination of these rows by keeping the same information distance of the original Reed-Muller code. So we add an additional information bit without changing the minimum distance. So for instance, if we take the code 128.99, okay, so this information set is chosen like this. The minimum distance of the code is 8. But we can add an additional information bit to this code by adding the third rows of information and by setting this frozen function without changing the minimum distance of the code. So we have increased the rate by 1 bit, but still we have 1 bit larger of the information set. Okay, so we have another result with common 1 bit position at B, I, G, and K, and the same kind of results holds. So I won't spend too much time on this. Okay, so we have proved that for a code whose binary representation, some rows whose binary representation have common 1 bit in some position of the binary representation, for instance, on the 6-1, we can carry an additional bit information by merging these rows, okay? And in that case, we don't reduce the Hamming weights of the minimum distance of the code. Okay, so these two, will it go? Okay, perfect. I don't need 10 minutes more. So, so these two first results allow to prove the final results of the work, which is this one. So by considering some triples with common 1 bit position and a theta left circular shift of the binary representation, theta belonging to the interval 0 kappa, where kappa is the summation of the number of common 0 of the binary representation of the triple plus the common number of 1 of their binary representation, then we can add up to kappa plus 1 information bits by merging the original row triples and the theta left circular shifts of this row by keeping the same minimum distance. So for instance, for the previous code, 128 and 64, minimum distance equal to 16. So let's take IGK equals 69, 74, 112. So we have the binary representation of this triple like this. So I naught is equal to 0. They don't have any common 0 in their binary representation. They have one common bit at 1 in their binary representation. This is here. So in that case, kappa equal 1. The one left circular shift of this binary representation are these. And we can construct the code 128.66, so with 2 additional bits, without sacrificing the minimum distance of the code. So that's the main result that we proved in this way. So if we pass, I have one simulation result to show, so we have no time to explain it. So in this figure, we compare the proposed scheme. So it is for a block length equal to 128. PD is a proposed design. In green curve, this is a pack code of Arican. And in dash line, this is the saddle point approximation of the meta converse that presents Samir this morning. Okay. So we see that for these particular code rates, okay, the proposed design is better than the proposed pack code design. Okay, for a convolutional encoder equal to 7 and optimized for this code parameters, and we are not so far away from the converse bound of the saddle point approximation. Okay, so this is time to conclude. So in this work, we propose the constructive method to modify the polar encoding, to precode the polar code in order to preserve or increase. It depends. We have another paper in ICC 2022 that was to increase the minimum distance instead of adding additional bits. So to shape the minimum distance of the underlying Reed-Muller code. So the analysis has been done by partitioning the code word bit indices. So it is closely related to the binary representation of the code. And it performs relatively close to the meta converse compared to the pack codes with respect to this parameter. So of course, we have been also tend to compare with 5G codes. So we have some results. I didn't include them in this presentation because we need to consolidate them first, but it's promising result at least for this set parameters. Okay, it does not perform better for all information length and all code word length, but at least for the one test, it seems to be better or close to. And that's it. Thank you.